Assalamualaikum. I hope you guys are doing well and I hope you had a good day. Alright, so this is day 2 of moles. Let's start. So the idea where we left off was that how do you convert the given information into moles? Like how do you figure this out? And one thing that we were talking about was that anything, if you weigh it and you get its mass, you can obviously divide that mass in terms of how many different moles you can have or how many different compounds uh, of the same MR, how many masses or groups of the same MR you can get, right? So that's the idea of having an MR and a mole. And we talked about three things. We said that number one, a mole is basically just another way of figuring out a certain amount, and it's equal to Avogadro's number of particles. Sorry. So that means that if you have 6.02 into 10 power 23 particles, that is 1 mole. But I did not expand upon that. Are those particles ions, atoms, or molecules? So that is something that we'll explore today. Similarly, we said that it is also equal to mR grams, and that is mR grams, right? So that means you need to know what the mR of that thing is. Now, what if I don't know the mR? Then can this still help me out? Of course it can, and we'll talk about that as well. And lastly, we said that there is 24 dm cube of the volume if it's a gas. And we left another thing out, that what if it was not a pure thing? Like these are all good for pure things. But what if it was a mixture, like an acid solution? What would we do in that case? So those are the three things that we need to know after today. And inshallah, we will be able to figure that one out. All right, so let's start with the first idea that do the same number of moles have the same number of particles? And does it matter what particles you're talking about? Because we know from our previous lessons that particles can be atoms, particles can be ions, and particles can be molecules. So those are the three different kinds of particles that we get. Alright, so obviously it makes it really important and it's very imperative that we know what particle we are talking about and how many of those moles do we have. Now here's the thing, you have to understand that a mole of anything will not care about what particles you have. It will just be Avogadro's number of those particles. So you have to see what that thing is made of. So for example, if I say iron and I say 1 mole of iron, that will be iron atoms because iron exists as atoms. But if I say H2SO4 or H2O, then H2O, which is water, it exists as molecules. So I will just have 1 mole will have 6.02 into 10 power 23 molecules. Similarly, if I had just ions like sodium ions, that would be just 1 mole of sodium ions. But things are made of different atoms. Things are made of different ions. So for example, if you look at water over here, then water has 2 hydrogen atoms and 1 oxygen atom in 1 molecule. So that means you just multiply that number. So if I have 1 mole of water, how many moles of hydrogen atoms do I have? 2 moles, because 1 mole has 2 hydrogens, 1 molecule has 2 hydrogens. So 1 mole will have 2 hydrogen atoms. This is just like saying I have 1,000 molecules of water. How many hydrogen atoms do I have? So of course I have 2,000 hydrogen atoms in 1,000 water molecules, and that is again just the same idea. So if you have for 1,000 moles or 1,000 molecules, it's the same thing for 6.02 into 10 power 23 molecules. It will be just multiplied with 2. Similarly, if I say that I am talking about sodium chloride, then every sodium chloride formula unit has sodium ion and chloride ion. So because one sodium chloride unit has 1 sodium ion and 1 chloride ion, that would simply mean that you will have for every sodium chloride formula unit, you get 1 sodium ion, 1 chloride ion. So how many total ions do you get? 2. So 1 mole of sodium chloride will have 2 moles of ions, 1 mole of sodium ions, 1 mole of chloride ions. What about H2SO4? Let's see. So H2SO4 is basically made of 2 hydrogen ions and 1 sulfate ions. Alright, so if I dissolve this in water, if I take 1 molecule of H2SO4 and I dissolve it in water, I will get 2 ions of hydrogen and 1 ion of sulfate. So how many total ions do I get? 3. So if I get 3 ions from 1 molecule of H2SO4, so from 1 mole I'll get 3 moles, right? So that is how it goes, that whenever something breaks down into different particles, the number of moles obviously multiplies with it, because every molecule is breaking down into 3 for H2SO4. So every mole will also break down into 3 moles of that thing. So that is why it matters what particles you have. So you just multiply it by that number. The second point that we wanted to talk about was, what if we do not know the MR? Can it still help us? And for that, we have a method and we have to understand that technique, which is called finding empirical formula. Now, things we show them, we communicate in terms of different formulas. So we can have molecular formula, we have empirical formula, and in covalent substances we have many other different kinds of formulas. Like we could have structural formula, we could have we could have a displayed formula, we could have 3D formula, we could have many different categories, and we'll talk about that when we study organic chemistry in particular. So what is the main difference in molecular and empirical? Turns out that molecular shows all present atoms. So it tells me all the atoms that are present in any molecule, in any compound. So this is what it tells me. So for example, when I say water, it's telling me H2O. In this case, this is the formula for 1 molecule of water. What that means is that it's telling me that I have 2 hydrogen atoms, 1 oxygen atom in 1 molecule of water. But if I talk about, let's say, H2O2, this is a totally different compound, hydrogen peroxide. And this one is telling me that I have 2 hydrogen atoms, 2 oxygen atoms, and they together make up 1 molecule of this thing. Now, empirical formula is slightly different. Empirical formula gives me the simplest ratio of all elements, basically all kinds of atoms. So for water, the ratio is still the same. There's double the hydrogen compared to oxygen. But for hydrogen peroxide, the ratio is not the same. You have equal number of hydrogen and oxygen. So we say HO. Yes, very good, Harun, very good. So it is the simplest ratio of all the elements that is present over here. So in this case, this is going to give us the empirical formula, and this is giving us the molecular formula. And as you can see, they're both the same, right? For water, they're both the same, but for this thing, hydrogen peroxide, it is different. Now, empirical formula and molecular formula also relates to MR. Now, the molecule, the mass of one molecule is MR, right? So if you take 1 molecule of water, it has 18 atomic mass units as its MR, and that is also the mass of this empirical formula. We call it empirical mass. So for water, because the empirical formula and molecular formula is the same, empirical mass and molecular mass is also the same. But for hydrogen peroxide, the empirical mass is 17 and the molecular mass is 34. Now this is interesting, because how do I get from H2O2 to HO? I just divide it by 2, right? That's how I get the empirical formula. So why wouldn't I get the mass if I divide the mass by 2? Or in other words, if I multiply this formula by 2, I get the molecular formula. And if I multiply the same mass, empirical mass by 2, I get the molecular mass, MR. So that's an interesting relationship. Basically, this number that I'm multiplying with, this 2, is called the ratio. It's the multiplicating factor that we have. So this number is basically the ratio between molecular formula and empirical formula, and this is the same ratio for molecular mass and empirical mass. So that gives me a very interesting factor. If I know empirical mass of something, or I just know the empirical formula of something, and I know this ratio, I can figure out the MR. It's that simple. Let me take an example. Let's say I have this compound, glucose, C6H12O6. What would its empirical formula be? C1 H2 O1 because the ratio is 1 to 1. 6 times 12 and 6. So that is 6, 12, 6 all divided by 6, 1 to 1. Alright, now this is the empirical formula, that's the molecular formula. What is the empirical mass? It is 1 carbon 12, 2 hydrogen 2, 1 oxygen 16, total 30. And if I multiply that by 6, I will get 180. Is that the MR? Of course it is. The MR is actually the same number multiplied with the empirical mass. So this can actually help us figure this out. So let me take an example from your one of the past paper questions, and there they told us the empirical formula. In fact, they found a way to figure out the empirical formula, and then they said that all right, now figure out what the compound is or what its actual formula is. So it's actually really easy. Just give me a minute, I'll get that question here. Yeah, got it. All right, now one thing that we can use is percentage mass to do this. So what is percentage mass? Again, that's a slightly off topic, but we'll come back to this. All right, so here's the thing. Percentage mass is what percentage of anything is made of a certain element. So for example, if I say we use urea is CONH2. This is a compound that is used as a fertilizer. Now plants need nitrogen. I want to know how much nitrogen plants will get if I have 1 mole of this thing or 1 kg of this thing. I want to know that. So for that, what I'll do is I'll first figure out the MR of this thing. Okay, so I have 1 carbon, 1 oxygen, 2 nitrogens because this is 1 times 2, that's 2 nitrogens, plus 4 hydrogen because 2 times 2, that's 4 in total. The total comes out to be 12 plus 16 plus 2 times 14 from the periodic table plus 4 times 1. Now let me add it all up. So 12 plus 16 plus this, that is 60. So its MR is 60 atomic mass units. All right, fair enough. Now how much of that is nitrogen? If I have, this basically tells me that if you have 60 grams of this, a certain percentage is going to be nitrogen, a certain percentage is going to be carbon, and so on. I want to know how much of nitrogen is present for the plants. So what will I do? The part for the nitrogen is this one. This is the mass in this thing that is coming from nitrogen. So I'll take that. So I'll take percentage of nitrogen. I'll take 2 times 14, that's 28, divided by 60, the total MR, multiplied by 100%. So if I do that, I will get, that is 46.7%. So what is this telling me? That 46.7% of this total mass is nitrogen. So if I have 1 kg of this thing, 467 grams will be nitrogen. All right. So if I take a ton of this thing, 467 kgs will be nitrogen that you're giving to the plants, right? So that's called percentage composition or percentage by mass. Now here's an interesting thing. What if I knew the percentage of everything? Would I be able to figure out the total? Would I be able to figure out the total formula, the total mass? Of course. If I told you that paper 1 is for 30% and paper 2 is for 60% and paper 4 is for 10%, let's say that's a combination, and I also told you that the total marks are 180, wouldn't you be able to figure out that what's the marks for paper 1, what's the marks for paper 2, and what's the marks for paper 3 or paper 4? Of course you will, right? Because you know 1 is 10, 1 is 60, 1 is 30, the total is 180, so 10% of that is 18, so that is the marks for paper 4. Similarly, 60% of that thing, whatever that comes out to be, that is 108, so you'll know paper 2 is for 108 marks, and the remaining you will know that that is 30%, so that is going to be 48, so that's the marks for paper 1 or something like that, right? You can figure that out just by knowing the percentage of your papers. So why can't we do it for elements? Of course we can. If I knew the percentage by mass of every element in there, I could actually come back and get this formula. Let me try that. What if I had percentage of hydrogen here? That would be 4, this 4 divided by 60 in total times 100%, which will come out to be 4 divided by 60 into 100%. That is 6.7 or 6.67%. Similarly, percentage of carbon, that is 12 over 60 because there's one carbon into 100%. So that's going to be 12 divided by 60 into 100%, that's 20%. And lastly, you can figure out the percentage for oxygen either by taking the mass or just add all of them up and subtract from 100. So if I have oxygen is 16 over 60 times 100%, that gives me what? 26.7%. All right. Now I have that percentages. If I did not know the formula, will I still be able to get it? Of course. Imagine I had 100 grams of this thing. So I had 100 grams of this thing. I do not know the formula, but I have 100 grams of this. And I also know what percentage of it is that. So I know there is carbon, there's hydrogen, there's oxygen, there's nitrogen, and I know the percentage. So if I had 100 grams, I would get 20 grams of carbon. Why? Because 20% is carbon. So 100 grams, 20 grams, right? Similarly, hydrogen would be 6.67%, oxygen would be 26.7%, and lastly, nitrogen would be 46.7%. Let me see if this all actually adds up to 100 or not. Yeah, it's slightly more than 100, but that's fine. All right, so we approximated. That's the reason it has slightly more than 100. All right, so here's what we'll do. The first step that we're going to do is we are going to take out the moles of carbon, hydrogen, oxygen, nitrogen. How do you figure out the moles? Divide by its AR. Notice it's not nitrogen molecule, it's nitrogen atoms. It's not oxygen molecule, it's oxygen atoms. So we'll divide this by 12, it's AR, this by 1, it's AR, this by 16, and this by 14. All right, so if I do that, what do I get? 20 divided by 12, that is 1.67. 6.67 is already there. Then 26.7 divided by 16, that is 1.67 again. Then nitrogen, 46.7 divided by 14, that is 3.33. Fair enough. Now this is the moles of this thing in 100 grams. All right, next step, simplify this. So this divided by the smallest number, because smallest number can easily divide them all. Doesn't always happen, but usually it does. So this will give me 1, this will give me 1. This one is going to be 4, and that one is going to be 2. So there you go. My ratios tell me that I have C1O1 N2H4. That is my empirical formula. Now, what if this did not work out so well? What if I had some weird number like a fraction? Could I approximate that? So let's say I had 1.5 somewhere, or I had 1.3 somewhere, or I had 1.7. I couldn't simplify that. Remember this. You cannot approximate that this is 2 and that is 1 and that is also 2. No, you can't. What you should do is convert it to a fraction. All right. So this one is simply 3 by 2. This one 1.333 going on. That is 4 by 3. This one 1.677 and all that. That is basically 5 by 3. Right? So what do? Once you've converted it to fraction, multiply by LCM. So basically I'm saying that after this thing, if you don't get whole numbers, you get fractions. Convert them to fractions and multiply the whole thing by its LCM. All right, so that's the key. You cannot approximate every number. Sure, if you have 1.1, it might work, or 1.99, you can write that is 2. But if you don't have that, if you get a fraction that's midway between one number or the other, or in thirds, or in fourths, or in fifths, then don't approximate. Multiply by the LCM so that you get a whole number. And that whole number will tell you the empirical formula as this one has in this case. Okay, so I know the empirical formula. Can I still figure out the molecular formula? Of course. How? Let's go back to where we started. We said molecular mass divided by empirical mass gives me the number n. And that same n is, for example, in the case of glucose, 6 multiplied by 30 is 180. 6 multiplied by CH2O is C6H12O6. It's the molecular formula. So if I'm able to figure out the ratio between molecular mass, MR, and empirical mass, that will give me this ratio. Just multiply the damn ratio by that ratio by the empirical formula and you will get your molecular formula, right? So that is the relation, and that's a very remarkable thing to do. So let's try an example of this thing. I need to know MR, of course, to figure this one out. So let's do an example. Okay, here we go. This is a question that says that find out the empirical formula and molecular formula that contains 62.07. The percentages are given. Okay, so what's the percentage? Carbon, hydrogen, nitrogen, oxygen, and percentages are this one is 62.07, this is 10, this is 14. What will be oxygen? Add them all up and subtract from 100, right? So 100 subtracting that gives me 13.93. All right, so that's the percentage mass. Now take 100 grams of that thing. That same percentage mass is now your actual mass. Now what's the first step? First step is to find moles. So divide by its AR. So this by 12, this by 1, this by 14, and this by 16. All right, so I do that. So 62.07 divided by 12, that gives me 5.17. That is 10, that is 1, and that one is 0.87. Now divide it all by 0.87. Simplify this. So just by 0.87, this by 0.87, this by 0.87, and of course this by 0.87. All right, when I do that, I get 1 here, and here I get 1.15, and here I get 10 divided by 0.87. I get 11.5, and here I get 6. All right, now this is a very weird combination. We'll just approximate in this case because we already have the things that we need, or we can divide it by, convert this to a fraction, and 11.5 divided by, if I divide that, that's 23 over 2, and that's nitrogen is again 1. So it's a very tricky situation. I'm just going to go with approximating this, okay? Because you have to consider the situation, the trade-off, all right? Sometimes you have to approximate. Sometimes the values are not that reliable, so you just take that value. So there you go, C6H12NO. That's my empirical formula. Now let's see, C6H12NO. What is the empirical mass? All right, let's figure that out. So 6 times 12 plus 12 times 1 plus 14 for nitrogen and 16 for oxygen. So 14 plus 16 plus 12 plus 72, that is 114. All right, so this is my empirical mass. All right, so I have my empirical mass. How does this relate to molecular mass? Let's see. My molecular mass is also 114. Interesting. So in this case, not approximating was the right thing. Approximating was the right thing to do. So it's saying that molecular mass is 114. Empirical mass is also 114. What's the ratio? 1. That means this thing multiplied by 1 is my molecular formula. So in this compound, my MR and the empirical mass is the same, which means the ratio is 1. And when the ratio is 1, the empirical mass and empirical formula and molecular formula, they're both the same thing. Now, there are cases where this might not be the case. What if they said that it's MR? What if the MR came out to be 342? Let's say that was the case. Then we will need to figure out the ratio first. So we'll divide the MR by 114 to get the ratio, which is 3, right? Now I'll multiply the empirical formula by 3 to get my molecular formula. So this multiplied by 3, that gives me C18, H36, N3, and O3. So in this case, when MR was 342, my ratio will be 3. And if my ratio is 3, my molecular formula will be different. But if my ratio is 1, molecular formula and empirical formula are the same thing. All right, so that is how we know how to convert, how to find percentage mass, how to find empirical formulas, how to use empirical formula to find molecular formula, and it all depends on this relation that molecular formula and empirical formula have the same factor as the MR and empirical mass. All right, then of course, knowing that if you split one molecule or one particle into multiple ions, the number of moles also multiplies just like that. So that was moles for today. I will see you tomorrow with stoichiometry. All right, if you have any questions, feel free to tell me. All right, okay, so see you tomorrow. Feel free to pose your question in the comments, share with your friends, subscribe to the channel. I really appreciate all the help that you give. Take care.